All right, so I want to show you an example of how to use this heat transfer equation before you give it a shot yourselves. First, though, I want to highlight a couple things in the equation for you to make conceptual sense of how to use it and what these things mean. There are 5 things in the equation, and I'm going to go over all of them, moving left to right. So first we have K, and K is a value which refers to the thermal conductivity of an object. It's what makes hot metal feel hot, and something like wood not feel hot even when it's the same temperature as the metal. So metals tend to have high K values. It depends on the metal, but values around like 200, and that conducts a lot of heat. Wood, for example, it would depend on the wood as well, but around like 0.13. So same temperature, you're going to transmit or transfer way less heat with a smaller K value. Next is A, which refers to the area of contact. So for example, if you have something and you contact it with a small area, you have a small heat transfer. Whereas if you have a large amount of contact, you have a lot of heat transfer. And you can think about this like on your stove. There are those smaller heating elements, and things generally take longer to heat up on them because there's less area contacting your pans. So if you can get a greater area of contact, you get greater heat transfer, which depending on what you're doing, sometimes you want and sometimes you don't. So T1 and T2 are both temperatures, and they refer to the two temperatures in question. Because anytime you have heat transfer, you have temperatures of 2 different objects. If the objects are the same temperature, lovely. If the objects are the same temperature, then they don't transfer any heat. So what matters here is not so much how hot a singular object is, but the difference in temperature between the two of them. If you have, a thing of metal at like 150 degrees, but the room is 90 degrees that it's in, you're gonna have way less heat transfer than if you take that thing of metal and put it on ice. Ice is way colder, and so you're gonna have way more heat transfer through that ice, also thermal conductivity. But let's just focus on differences in temperature. And then finally we have at the bottom of the equation D, which refers to the thickness. And this is thickness of like a barrier in between 2 objects exchanging heat. So for example, when you put on like an oven mitt, that is going to be a barrier between your hand and a hot pan coming out of the oven. If that is thicker, then you have less heat transfer because it's on the bottom of the equation. So everything on the top of the equation, those things get multiplied, and so the bigger they are, the more heat transfer you have. Everything on the bottom of the equation is divided out, so bigger numbers on the bottom are going to have a smaller heat transfer. Okay, so we're going to look at a sample problem, and I'm going to work it through with a video feed on my phone so that you can see me working through it. I'm going to read through the question. I haven't decided yet how I'm going to put this up. You'll know because you're watching this video. But either way, go ahead and pause this video, screenshot the question, or write it down so you can track it while I go through the problem. So the problem we're going to be going through to use our new heat transfer equation says the air in a room is at 25 degrees Celsius while the outside temperature is 0 degrees Celsius. In one room, there is a window with an area of 2 square meters and a thickness of 5 millimeters. Calculate the rate of loss of heat by conduction through the window. Assume the thermal conductivity of glass is 1. So, as is always the case, we want to write down all of our givens. So we have K, and we were told that the thermal conductivity of glass in this scenario is 1. We have A. A is the area, and heat is being transferred through this glass, and it has an area, we were told, of 2 square meters. T1, let's just use the first temperature that was given to us, and that's going to be 25 degrees Celsius. And then T2 is the second temperature that was given to us, and that's going to be 0 degrees Celsius. And then the last thing we need is the thickness of the barrier, thickness of the glass. We were told that it was, 5 millimeters, but what we really want is 0.005 meters. Unless I tell you otherwise, always plug in SI values into physics equations. Okay, so we have all of our givens. Now we're just plugging our givens into our equation. So we have 1 for K, we have 2 for A, we have our 2 temperatures, so that's going to be 25 minus 0. And then we're going to take that all over the thickness of the glass, which is 0.005. let's simplify this. 25 minus 0 is 25 times 2 is going to be 50. We're going to divide that by 0.005, and that's going to give us 10,000, and that's going to be in watts. So watts, as we've learned, should be joules per second. So it's the amount of energy that is flowing every second. Hopefully that makes sense. And this is a pretty big number. And I intentionally picked, for contrast, as you will see, numbers that would provide contrast. So this is a stupidly thin window. Windows are rarely that thin, and they're also rarely single panes anymore. So let's do example problem number 2. So we're going to be using the same equation. And again, same deal, you might want to pause, write down the problem so that you can look at it while I go through this. But the problem says you have a styrofoam cooler with a total surface area of 0.54 meters with a wall thickness of 5 centimeters and a thermal conductivity value of 0.03. You have ice inside the cooler, keeping it at a temperature of 0 degrees Celsius. If the temperature outside is 30 degrees Celsius, what will the rate of heat transfer be out of your cooler? Okay, so we're going to run through the same thing. As is the case with lots of physics problems, the biggest struggle is identifying the givens in your problems, which I'm giving you easy ones to start with. So we're going to have K, our thermal conductivity, is going to be 0.03. A, the total surface area, is going to be 0.54. T1 is going to be 30 degrees. T2 is going to be 0 degrees. And then D is going to be 5 centimeters. So now it's 0.05 meters. All right, sorry about that. The thickness is 5 centimeters or 0.05 meters. So again, we're just plugging things in and getting an answer. So we're going to have 0.03 times 0.54, 30 minus 0, all over 0.05. I'm not going to crunch all of the exact numbers for this. You can do that if you want with a calculator step by step. I'm just going to tell you that you get 9.72 watts. So here's the thing that you should be keying into. One, we would expect this value to be lower because it seems way more insulating. But why? Why is it being driven? What is driving this equation to make it way more insulating? So there are really two things that I can really point to that are going to matter a lot. One, the thermal conductivity is way lower, like significantly lower, less than 10 times the value of glass, which is why we use styrofoam and we don't have glass coolers or metal coolers. That would be dumb. And then the thickness as well, the thickness is 10 times greater than the thickness of the window. And honestly, this is going to be way more like modern insulating windows are going to be like. So you're not going to see that crazy value from before. But I wanted you to see a really big number with heat transfer and then a really small number with heat transfer to show that, that contrast. So hopefully this made sense. Hopefully this was trackable. You're going to practice now on your own. And please do not hesitate to reach out if you have any questions. I'm more than happy to walk you through. Yeah, take care.